Hi, I am Sushanto. In this session, I will find the current through the load resistance RL of 4 ohm using Thevenin's theorem. Now, this is a purely resistive network with two independent sources, one voltage source, one current source, and clearly it is a linear network and Thevenin's theorem can be used. Now, using Thevenin's theorem, we can reduce the entire network other than this load resistance. So, think about the remainder of the network other than the load resistance. So, this entire network other than the load resistance can be reduced to one voltage source of EMF V Thevenin and one resistance R Thevenin. So, this is an ideal voltage source. So, ideal voltage source we know does not actually exist. So, these two together are basically parts of one Thevenin cell or one Thevenin source. So, the Thevenin cell will have the EMF equal to V Thevenin and internal resistance equal to R Thevenin. So, these two together is just one cell. So, the entire network other than the load resistance is reduced to just one cell with EMF equal to V Thevenin and internal resistance equal to R Thevenin, and this R load is connected across that cell. So, this is R load and connected here, and the rest of the circuit is just one cell. That is what Thevenin's theorem does. And so, let us find V Thevenin and R Thevenin. So, how to find V Thevenin? To find V Thevenin, we first remove the load resistance from here. So, we remove the load resistance. So, A and B, the 2 points are not connected anymore. So, there is an open circuit voltage between A and B. So, this open circuit voltage is basically V Thevenin. So, V open circuit, this is equal to V Thevenin. So, you have to find the open circuit voltage. So, for that we first assign some current to all the branches. So, this is I. So, the same current flows here I, and this I comes down, and then this 3 ampere and this I get added up. So, we use KCL at M and get that the current here is I plus 3. Then this same I plus 3 flows down here, and then at N it gets split into I flowing back to 6 volt cell and 3 ampere flowing back to this current source. Now, we apply KVL to this. So, we apply KVL to QP M B N and Q. So, we apply KVL to QP MB NQ loop. So, from here we start with 6 volts, and then I times 2 omega, that is I times 2 is dropped here, and then I plus 3 flows through 3 ohm and 1 ohm, that is 3 ohm and 1 ohm are in series. So, I plus 3 basically flows through 3 plus 1, that is 4 ohm. So, I plus 3 times 4 is dropped between M and N. So, ultimately at N we are left with just 0 volt, which is the voltage at this end of the cell. So, this is equal to 0. So, that is KVL equation for this loop. Now, so this is 6 minus 2I minus 4I minus 12 is equal to 0. Now, 6 minus 12 is minus 6, minus 2I minus 4I is minus 6I is equal to 0. So, 6I is equal to minus 6. So, I equal to minus 1 ampere. So, the negative sign indicates that the current direction assumed here was wrong. So, current should be flowing like this, downwards here to the left here and up here, but it does not matter if we keep this direction and this negative sign in our further calculations, we will get everything right. So, now we have to find V Thevenin. So, for that we use this loop. the smaller loop. So we use KVL on AB and A. We use KVL on AB and A. So again we start with 6 volt. Then between A and B, Thevenin is lost, so minus Thevenin. And then as the current flows down from B to N, so I plus 3 times 1 is lost across this 1 ohm resistor. And then we are back to this 6 volt, so with 0 volt. So this point is 0 volt and this point is 0 volt. So this is 0 volt, this is 6 volt. So as the current reaches this point, it's left with just 0 volt, and that is what is shown on the right hand side. So 6 minus Thevenin minus I plus 3, now I is minus 1. So 6 minus Thevenin minus, this is minus 1 plus 3 is equal to 0. So 6 minus Thevenin minus 2 is equal to 0. So Thevenin equal to 4. So 4 volts is this voltage, so Thevenin is equal to 4 volts. Now next we have to find Thevenin. So to find Thevenin, we short circuit the independent voltage source. So as we short circuit independent voltage source, we can just remove this independent voltage source and replace it by a zero resistance conductor. So I just replace it by a zero resistance conductor, and we also remove the current source, that is open circuit the current source. So everything here is removed, so there will be no current flow anymore. So this is what the circuit now looks like. So between A and B we have this 2 ohm and 3 ohm resistance connected on one side of AB. So the circuit now looks like this. This is A and B. So 3 ohm and 2 ohm are connected in series. So it's 2 ohm and then it's 3 ohm, and the other one, that is 1 ohm, is connected to the other side of AB. So this 5 ohm and 1 ohm are in parallel. So this is 5 ohm and this is 1 ohm. So the equivalent resistance, which is Thevenin between A and B, is 5 times 1 divided by 5 plus 1, that is 5 over 6 ohm. So Thevenin is 5 over 6 ohm. Now this is the whole circuit. So we have to find the current through this load resistance. Suppose the current through this load resistance is IL. So this 4 volts is equal to, so 4 volts equal to, 4 volts is Thevenin voltage, is equal to IL times Thevenin is 5 over 6 and R load is 4. So 4 is equal to IL, then this is 24 plus 5, that is 29, 29 over 6. So IL is equal to 6 times 4, that is 24 over 29 ampere. So 24 over 29 ampere current flows through the load resistance, which is connected between A and B in this linear network, and this current is found using Thevenin's theorem, and the current is 24 over 29 ampere.